Hi, so today I'm going to be doing Codechef. So this was some starter 82 round, codechef.com/problem/tree game. Let me just check what is being shared. Yeah, so I will explain what the problem is, and I think I just want to go over the editorial. And I mean, I tried this for a while and I don't have a way to do it, so I should be sharing this. Yeah, okay. So here the idea is you have like a tree graph. So, and you have all of these edges, okay? And oh, yeah, it's a tree. It's not, you don't have multiple paths. And you have a population at each edge, say 5, 10, 15, 20, right? 7, 8, 9. Then you have Alice and Bob. They start, oh, sorry, A and B. I think they didn't call them. Oh, Alice and Bob. Okay. So they start at so Alice starts, say, at this city and Bob starts at this city. At each turn, they can move to any of their of their neighboring cities, and but they can't move back to a city they've already visited, or they can't move back a path they've already visited. So the way it works is A makes a move, then B makes a move, then A makes a move. So A can go to where B has gone, but it just can't go back to where it has gone, and so on. And what A is trying to do is at each turn, once A makes a move and B makes a move, the total population travel till now is counted. So for instance, if A goes from this position to this position, total population till now is 15. If B goes from this position to this position, the total population is 35, right? If A's total population is greater than B's total population, then A gets a point, right? Otherwise, A doesn't get a point. So every turn they check the total population so far. So after this, if the second move, it might be like what, 5 plus 10, 15 plus 15, 30, and so on. So it just keeps accumulating, right? And A will try and play the game optimally to make the move such that she gets the maximum score. And B is like against A. So B will try to play the game optimally to make it such that A gets the minimum score, right? So given both of them play optimally, what is A's final score? So that's the question. We can do an example that is here. We can do that they gave. So um, 6. Oh, those are their initial positions. That's the population. Okay, so there are 6 nodes. 1, 2, 3, 4, 5, 6. This is the population at each node. Um, right? And these are the edges. 1 to 2, 2 to 3 to 2, 4 to 2, 6 to 4, and 4 to 5. Okay. And A's position is here at 2 and B's position is 4. Okay. So in the first move, I mean, if A makes a move, it makes sense for A to, oh, okay, A has these moves as well. So what do they do? I guess B will just go here to finish A's game, and A will go here, I'm guessing. So yeah. Um, okay. So if A goes here, she gets a total score of 6. And if B goes there, total score of 5. So 6 is greater than 5. So A gets 1 point, and then the game stops. If they can't travel anymore, game stops. So A gets 1 point. Now, it might be tempting to think here that you can. So one option is um, for a given A path, like for a given path of A, minimize over all possible paths B can take and minimize the total score. So minimize over B paths, score of A path comma B path, right? This, and then maximize this overall A paths. So I mean, a lot of this is due to like I was discussing with a friend Pratik Sani, and his Discord will be in the description. This and an example later. So this, you might be tempted to do something like this. So that is like basically take all pairs of paths, right? And for each A path, find what B will do, and then find what A will do, right? This maybe might have worked if um if it was like a one-step thing, right? Okay, how do I explain this? Okay, if for every path A could take, B was able to do the minimum, then this might have worked. But over here, it might turn out that for a certain path A takes, B might not know beforehand which path A takes, and might make some choices such that B is unable to do the minimum, right? So the sort of example we came up with for this was um, so imagine that. So we were able to put, like, I don't have the numbers. Yeah, we were able to put numbers and make this better. But imagine A is here and B is here, right? Something like this. So B has to like make a choice right here. So A goes here first, and B has to make a choice right here, makes one of these choices. It might turn out that if A takes this path, this is actually the path that B was supposed to take, but B doesn't know that beforehand. So because B is unable to, for every A path, B is unable to minimize it, this idea doesn't work. And you might have to play it step by step. So yeah, I've been trying to write out the recursion for this, but I keep getting confused. So I'm just going to look at the editorial. So yeah, I'll go back to share in. I think they said all the editorials are somewhere. Oh wow, perfect. Yeah, so one thing they did was they'll pre-compute all the populations so far. That's nice. F of x comma y denote the best score if the game starts. Yeah, okay. From a state, the next state can be achieved. U is a neighbor of x and V is a neighbor of y. U doesn't lie on ax path and V doesn't lie on vy path. X fixes jaw. If Alice fixes her choice of U, Bob will choose V such that f u comma v is minimized. That makes sense, no? Um, yeah, because for the score so far, they can't do anything, but the rest of the score can minimize. So across all possible choices of U, to maximize her own score, Alice will choose the U such that minimum over V, f of U comma V is maximized. That makes sense. Writing in terms of f of x comma y is equal to maximum over U, minimum over V. Mm. F of x comma y is your score if you start the game at x comma y, right? So that is the score at u comma v plus the score, I mean, total score for u comma v plus the score on this step. Okay, the score on this step is sax plus s greater, whether sax is greater than sby. Of n square possible states, not all of them are. We do of n by iterating all pairs of neighbors. I didn't get the O of n to the 4 thing. yeah, for each state, okay, n square states, and for each state we'll do n square work, okay. The transitions essentially consider a pair of edges. Yeah, however, the edge can be compared with another one at most 4 times. Transitions are a pair of edges, that's true. One that A's edge and B's edge, okay. Uh, each edge can be compared with another at most 4 times. What does that mean? No idea. This is a tree and which means the total number of transitions we make across all states is bounded by 4 into n minus 1 the whole square. Okay, let's maybe draw this down and see where we get stuck. So let's say in this problem only, first, okay, let me try to run the algorithm. First, we would have pre-computed all populations from A. So let's do that in orange. So this is 1 plus 5. So, oh, and from for B also we should have done that. Okay, I will write A in orange. 1 plus 5, 6. 1 plus 4, 5. 1 plus 2, 3. 1 plus 2 plus 2, 5. 1 plus 2 plus 3, 6. Janta. 2 plus 1, 3. 2 plus 1 plus 5. 3 plus 5, 8. 1 plus 2 plus 1 plus 4. 2 plus 3, 5. 2 plus 2. Okay. So now once this is pre-computed, you want to do all possible. You want to make a table. Oh, caching values of fx. Now for this, let's see how it looks. Oh, maybe a selection. Okay, it's fine. So what I care about is A's position being 2 and B's position being 4. So f of 2 comma 4. To compute that, right? Then this has 1, 4, 3. 1, 4, 3. And this has 5, 6, 2. Then I have 1, 4, 3, 1, 4, 3, 5, 5, 5, 6, 6, 6, 2, 2, 2. Right? And so on. 1, 5 depends on nothing. 4, 5. Oh, the game stops. Depends on nothing. 3, 5. This is fine. 6 also the game stops. 1, 3 the game stops. So the only 4, 2 is the only thing you need to worry about. A at 4 and B at 2. A at 4, there's 2 options. B at 2, there's another 2 options. So 4 options. So somehow they're saying that the number of computations we make is bounded by 4 times n minus 1 the whole square, which doesn't seem clear to me. So we can just do the brute force, that's the claim. Suppose yeah, they do 2 to 1, 4 to 5. It's the pair of edges. An edge. At most, that I don't get. Maybe there's some comments. Yeah. Yeah, I think I get how to code this. Maybe I'm being presumptuous. Let me Try to read what they're saying. No. One thing is, I feel like you can use the fact that you can't travel back to the same point, up the same point, right? So, what does that tell us? Um, yeah, I feel I'm getting nowhere with this. I'll try another question and think about this later. Guess this was the make them alike question. I'd submitted this, but I'd gotten it wrong. Yeah. Or actually, that's it for today. I don't think I can do any more.